The PDP research group was a temporary and informal association of over a dozen people, led by the American psychologists David Rumelhart and James McClelland. The introduction to Volume 1 of Parallel Distributed Processing, written by this group in 1986, explains that the work has been interdisciplinary and represents what we consider a true cognitive science approach. Although the two of us have been trained as cognitive psychologists, the PDP group as a whole includes people from a wide range of backgrounds. It includes people trained in physics, mathematics, neuroscience, molecular biology, and computer sciences, as well as in psychology. The introduction goes on to give a kind of thesis of this interdisciplinary project. A Cray computer can perform on the order of 100 million double precision multiplications in a second, but it does not exhibit natural intelligence. How then are we to understand the capabilities of human thought, given the time constraints and noisiness inherent in neural systems? It seemed obvious that to get any processing done in real time, the slow, noisy hardware in the brain would have to do massively parallel processing. They stuck with the phrase parallel distributed processing, or PDP for short, because it emphasized the parallel nature of the processing, the use of distributed representations and distributed control, and that general processing systems, rather than memories, were being studied. It's established early on in the book that serial processing mechanisms simply wouldn't relate to human cognitive abilities in any useful way. Serious attempts to model even the simplest macro steps of cognition, say recognition of simple words, require vast numbers of micro-steps if they're to be implemented sequentially. As Feldman and Ballard have pointed out, the biological hardware is just too sluggish for sequential models of the microstructure to provide a plausible account, at least of the microstructure of human thought. With this in mind, we can see the potential utility of parallel distributed processing in comparison to serial processing. The 1994 Nick Land text CyberGothic explains PDP as something which transcends temporality. While computational serialism articulates a transcendent temporal metric determined as a hardware specification, parallelism immanentizes time as duration, instantiated in machinic simultaneities. Unlike serial time, which serves as the extrinsic chronological support for algorithmic operations, parallel time is directly functional during the engineering of coincidences. CyberGothic also hints at an account of PDP as science fiction. We learn that cyberspace can be thought of as a system implemented in software, and therefore in space, although unlocalizable. It can also be suggested that everything designated by space within the human cultural system is implemented on weakly communicating parallel distributed processing systems, less than 10 to the 11th power nerve cells in size, which are being invasively digitized and loaded into cyberspace. This is suggestive of how, by applying principles of neuroscience and psychology to computing systems, parallel distributed processing blurs the boundaries between cognitive science and computer science. The PDP models used in the text were neurally inspired, with Rumelhart and McClelland specifying a desire to replace the computer metaphor with a brain metaphor as the model of the mind. A significant way in which they sought to diverge from the computer metaphor of the mind was in emphasizing the constraint that all the knowledge is in the connections. In the book, we're told that PDP models assume that information processing takes place through the interactions of a large number of simple processing elements called units, each sending excitatory and inhibitory signals to other units. This emphasis on connections between units, by the way, is why parallel distributed processing is almost synonymous with the term connectionism. The PDP book summarizes later on that from conventional computers, we're used to thinking of knowledge as being stored in the state of certain units in the system. In our systems, we assume that only very short-term storage can occur in the states of units. Long-term storage occurs in the connections among units. So, learning, rather than being a process of storing explicit rules within units, is thought of rather as a process of building up connection strengths between units based on information available at the connections. As I explained in my first video, The homeostat is a basic machine which circulates an electrical input current through a circuit until a uniselector in the machine alters its resistance to suit the current. After many iterations of resistance, through a kind of recursive feedback in the system, the input is converted to an output and an equilibrium is reached. This is the stability of homeostasis, which I believe forms the basic cybernetic ontology of many machinic systems, such as parallel distributed processing systems. The connections between processing units are classed as either excitatory or inhibitory connections, depending on how inputs affect the units. This can also be likened to the ontology of flows and blockages which we get in Anti-Oedipus by Deleuze and Guattari. To quote from Chapter 1, the productive synthesis, the production of production, is inherently connective in nature. This is because there is always a flow-producing machine, and another machine connected to it that interrupts or draws off part of this flow. And because the first machine is in turn connected to another whose flow it interrupts or partially drains off, the binary series is linear in every direction. Desire constantly couples continuous flows and partial objects that are by nature fragmentary and fragmented. Desire causes the current to flow, itself flows in turn, and breaks the flows. Now, let's look at the major learning mechanisms of PDP models. First, regularity discovery. This involves units learning to respond to noteworthy input patterns. Such a scheme should be able to form the basis for the development of feature detectors, and therefore the basis for knowledge representation in a PDP system. It's concerned with the meaning of a particular unit's response, and hence useful for discovering features of an input. Associative learning. This involves learning to produce a particular pattern of activation on one set of units, wherever another activation pattern occurs on another set of units. In this sense, an arbitrary pattern on a set of units will produce another arbitrary pattern on a set of units. Associative learning can be classed into pattern association, where the goal is to build up an association between patterns defined over one subset of units and other patterns defined over another subset of units. And wherever a particular pattern appears on the first set of units, the associated pattern will appear on the second set. And auto-association, where an input pattern is associated with itself, and whenever a portion of the input pattern is presented, the remainder of the pattern is to be filled in. Auto-association is similar to simple pattern association, but the input pattern acts as both the teaching input and the pattern to be associated. With an auto-associated paradigm, patterns which have been repeatedly presented to a system will be presented only in part, and the system will attempt to retrieve the original pattern through a pattern completion procedure. In this way, a degraded version of the original pattern can act as a retrieval queue. In auto-association, all units are both input and output units. As we can see in this diagram, a set of units will tend to feed back on itself through modifiable connections. Note again the relation to homeostasis. Another paradigm of associated learning is the classification paradigm, which involves a fixed set of categories into which the stimulus patterns are to be classified, and a training session in which the system is presented with the stimulus patterns along with the categories into which each stimulus belongs. A related paradigm is the regularity detector, which involves a population of stimulus patterns, and each stimulus pattern is presented with some probability. Rather than a pre-existing set of categories, as in the classification paradigm, the system is supposed to discover statistically salient features of the input population. The regularity detector paradigm is the ideal environment for comparative learning, which I'll explain here. Typical comparative learning system architecture, as shown in this diagram, involves a set of hierarchically layered sets of units. The units, represented here as dots, are either active or inactive, as indicated by the shaded and unshaded dots, respectively. Each unit within a layer will receive an input from each unit of the layer below, and will project an output onto each unit in the layer above. Within layers, these units create mutually inhibitory clusters, in that every unit within a cluster inhibits every other unit. The units compete to respond most directly to the pattern projected from the layer below, and the units with the strongest response shut down the other units. This type of interaction is known as competitive inhibition. One unit will win out over the other units in a cluster, and will receive an input pushing it to its maximum value, while every other unit will be pushed to its minimum value. Units can only learn if they achieve this value. A unit has a positive weight distributed among its input lines, and it learns by shifting weight from inactive to active input lines. In the comparative learning system, if there's any kind of structure in the stimulus pattern, the units will break the patterns up along structurally relevant lines. This is to say that the system will generally find clusters if there are any to be found. We're told in Chapter 5 that the particular grouping done by a particular cluster depends on the starting value of the weights and the sequence of stimulus patterns actually presented. A large number of clusters, each receiving inputs from the same input flows, can, in general, classify the inputs into a large number of different groupings, or alternatively, discover a variety of independent features present in the stimulus population. The PDP research group also states that, in our experiments, we started the weight vectors in random directions and presented the stimuli randomly. In this case, there's rapid movement as the system reaches a relatively stable configuration. Hence, the comparative learning system moves towards a homeostatic equilibrium. This diagram shows the units and the connections between units which we find in a PDP system. It also shows that each unit has an activation value, an output value, and a connection strength, represented by these weights. As we saw with comparative learning, the activation of a unit by the flows of its input lines is the most important thing about it. When restricted to discrete categories, activation values tend to be binary. 1 is active and 0 is inactive. Active is positive, inactive is negative. Positive is excitatory, negative is inhibitory. Returning to CyberGothic, we're told that if Wintermute replication is territorialized to the molar reproduction of a hive organism, this is only at the cost of deterritorializing the hive along a line of post-organic becoming toward a break from the statistical series of wasps, numbered bullets reiterating an identity, in the direction of molecular involution, releasing a cloud or nebula of wasps, particles of synergic mutation, numbering numbers. I see this passage as contrasting the discrete values of a binary input with the continuous or potentially unlimited values of a non-binary form of input. The machinic structure of the wasp hive operates in an ordered and numerical way, whereas the cloud of wasps is a more organic formulation. Where discrete values attenuate the potential variety in a system, continuous values maximize it, and can be more directly mapped onto real numbers. However, this is all in relation to activation levels, which are more often than not distinct, though related to output levels. At times, for instance, the output function can change if a certain threshold of activation is reached. At other times, the output function can be entirely dependent on the activation value. Anyway, that's my understanding of PDP and cybernetics. In the context of this video, the term parallel distributed processing denotes the research done in the 1980s in particular, but especially when considering the popularity of artificial neural networks and deep learning, it could be argued that PDP models in general were the first step towards the development of artificial intelligence as we now understand it. I would like to take a minute to thank the dozens of people that have subscribed over the last year or so, as it does make me excited about the future of this channel. I'll see you next time.